I'm very pleased to welcome Dr. Robert Jackson and yes. Yes. Oh yeah. Okay. Yeah. So, and then I've brought our speaker today, Dr. Robert Jackson. He is a passionate atmospheric scientist and software engineer who has either led or co-developer on multiple open source software projects for atmospheric data analysis. In addition, he uses data science tools and machine learning to gain insight from multi-terabyte climate data sets. And then also we are here today at the DPDI, sorry. And then here, I'll give it to our host, Sandra.
Thank you so much. And it's our pleasure to have you here. I'm Sandra Gesing. I'm one of the senior research scientists at the Discovery Partners Institute here in Chicago. That is DPI. And it has 3 departments. So the all-over mission is to start people's tech careers and companies and startups in Chicago and the Chicago area, Illinois. And with the 3 departments, so I'm from Applied R&D, so we do scientific research. I brought my own research to DPI, and that is science gateways, distributed computing, usability, research software, sustainability of research software. And we have 2 other departments who are very into workforce development, connections from really K-12 school systems to colleges, to universities, really to go the whole way through for the education part. And with that, it's my pleasure to give it to our speaker. And I give him also the microphone.
I think we've got a consent to being recorded. Everyone's name is Bobby Jackson from Argonne National Lab, and today I'm going to be talking to you about a Python package that one could use to do what we call multi-Doppler retrievals of winds from radar networks. So essentially, what the problem we're trying to solve here is we've got radar networks that are present all over the U.S., including the NextRad network that many of the people here, in fact, most people here probably looked at an image of a radar screen. We're trying to look to see how we get winds from those. And in particular, I would like to first thank my collaborators here listed on the screen for other contributions to this work. There we go. And now that we can see the screen up here, I also like to thank PyData Chicago and the Discovery Partners Institute for hosting the space to be able for me to give this talk, as well as the Department of Energy's Climate Model Development Validation activity for funding the work on this, as well as the Argonne Laboratory Directed Research and Development Expedition Program. So how do we measure winds? So there are many ways that we measure wind in the atmosphere. So one of the ways we do it is through point measurements from anemometers and aircraft. So these provide very accurate information about winds in the 2D space, an anemometer. But actually, you can even get 3D winds from anemometer, as well as the aircraft from a single point. However, the drawback of this is that this is only over a single point value, so you lack a lot of information about the structure of these clouds. In addition, we also get it from weather balloons. So there's a picture of me actually launching a weather balloon for a NSF field project back in 2009, where we sampled winter storms called plows, and also from radar wind profilers that will provide a vertical profile of the winds, but they're accurate to the meter scale resolution. But they only provide what we call a sonostraw view of the storm through the column. So we only are getting one little piece of the storm. You're not getting the full 3D picture of that. That's where we bring in a radar network such as what NOAA has, called the NextRad radar network. Almost everybody here has looked at the images from this radar. It is what tells us whether there's a storm coming, and it covers about 80% of the United States in terms of coverage, and it covers altitudes from about 0 kilometers up to about 15 kilometers up in the atmosphere. So it gives us much wider spatial coverage of these radar networks. And what these radars do is that they emit a beam of microwave radiation and record back the amplitude and phase of the backscattered microwaves as they spin around it. So what the NextRads in particular will do what we call plant position indicator scans, where they will spin in a 360-degree azimuth over one elevation, then go up to another elevation, and then repeat the 360-degree azimuth until you cover about 10 to 15 elevations, depending on what weather is present in the area. The National Weather Service actually changes what this volume pattern is. But then it wasn't that these objects such as rain, hail, and birds and planes and insects and smoke all reflect radiation back to the radar, and it all can be detected by it. What we're interested in more is precipitation. So we apply some quality control algorithms to remove what we call the non-hydrogen meteors, or anything that isn't rain, snow, graupel, or hail, anything we're not interested in. An example of some of this radar image is shown on the right. We have an example cell that passed over the Houston area here during one of our field experiments out that the DOE recently did over Houston. What we see here is a thunderstorm that forms in the early morning hours and lasts for about 45 minutes to an hour, going to the north over Galveston Bay and proceeding to the east of the Houston area. Now, one of the tricks about getting winds in particular from the radar is that the Doppler radar will record the velocity of particles in the direction in and out of the beam. It doesn't actually give you. One of the disadvantages of the radar is that while you get the full volume coverage, you only get the wind in the direction that is to the beam. And it's determined by the Doppler shift of the wave that comes in. So it just records the difference in phase between the incoming wave and the outgoing wave. And if this phase shift is greater than one wavelength, then the radar will record a negative shift and a negative velocity, even forcing velocity to flip sign. And if the velocity, which just happens, is called Nyquist velocity. So we have to correct for all of these different aspects of the Doppler velocity as well. For example, here we have a storm coming through, and we have an radar image of a storm coming through where we can see the Doppler velocity or the wind inbound going from 15 to -15. That is literally just an artifact of the radar we have to clean up with. And you can see it here where we apply these corrections, and then now we're able to get 20 meters per second velocities like it's properly recording. And we do this with tools such as the Pion Arm Radar Toolkit, called PyArt. And this is a toolkit that is developed by our group here at Argonne that is used for a variety of tasks, from basic plotting to more complex processing pipelines. And it can read radar data in a variety of formats, create plots and visualizations, and do corrections on the radar data, as well as writing radar data into a commonly used data format in the atmospheric sciences and geosciences called NetCDF. So first, what I'm going to do is I'm actually going to give a little bit of an introduction before I go to PyDDA. I'm going to go with an introduction about PyArt, and this is available through an NCAR unit data and University of Albany led project called Project Pythia, where their mission is provided basically accessible training resources for anybody wanting to use Earth science with a scientific Python ecosystem and to make sense of the huge volumes of data. So if we actually go here and click on the radar cookbook, this whole page here will show various examples of how to use the PyArt toolkit to view your radar data, as well as go over the fundamental basics of weather radar that anybody could come here to read at any time, and then see what we have here. So first, I'm going to go here, and I'm going to what I'm going to do is go to the radar cookbook, and I'm going to give it a. Actually, I have these same slides present in another tab. So we are giving. So this is what I'm slides I'm going to be presenting here. I'm going to show here a little later about a short course that we're actually giving next week in Minneapolis at the American Meteorological Society's radar conference. But this shows here is a cookbook on how to use this PyArt package to visualize your radar data, and it shows you the different prerequisites that into different packages as far as the basics of a CartaPy for visualizing of maps, and well-known packages within the PyData community such as Matplotlib and NumPy. So first, we have here our imports that we have here. So we do our proper imports, and this cookbook has all of the different packages already installed, and you can run it from the web anytime you want here. we do the imports. And what is Pyre? I already went a bit over what Pyre is able to do. It is an open source package for viewing radar data that anybody could, if anybody with an Anaconda could go ahead and install and do a conda install and then run on their own in their own environment. So to read in data, we just use a function compire.io.read. And what this does is that it reads a variety of radar formats. So these are different formats that the radar community has used over the years. Pyre will actually try to make their job easier, try to automatically detect this format for you so that you could go ahead and read the file. So we have an example file from the University of Alabama Huntsville's Armor radar that it's going to try and read in here. And it does here successfully by just using pyre.io.read. Now, if we look at the radar object, it stores the radar, the fields that are in the radar or the variables that it stores within these keys. So we know here that this radar is storing the total power, the reflectivity, which is the reflectivity map that you see on your when you look at the radar, velocity, which is going to be the wind direction here, as well as various other polarization characteristics of the radar that I won't have time to go into today. So here we look at the reflectivity, and it's stored as a masked array in the data key of this reflectivity structure. If we look at the shape, it's the number of rays, and the number, basically what we have is the number of rays that are sent out by the radar beam in one scan versus the number of gates or the number of pulses that are out for every radar scan. So this number of gates or basically tells you the distance for the radar, or what we call the range for the radar. So when we look at the 300th ray of the second gate, we can just look at that and say it's minus 4.5. But the coolest thing about this is that we can visualize these results using the graph radar map display object. And then we just do display plot PPI map. So what this is, this will plot the radar image of the lowest level for you. And give it a second. So this shows you a thunderstorm that's being scanned by the Armor radar. As we can see over here, we have some thunderstorms on the leading edge over here, and then another line here right behind it. So this is able to quickly make these visualizations here for you for radar data. If you wanted to grab from NextRad, or if you wanted to grab from any sort of other radar source, this could do it within just a couple lines of code. In default, it's going to plot, the default was the lowest elevation scan, and it also set these color bars of a range from minus 30 to 70. So let's go ahead, we could go in and adjust these properties by doing, let's say, the third elevation scan, as well as setting the color bar limits from minus 20 to 60 by just adjusting the Vmin, Vmax, and sweep. And now we can see that the color bars represent the range of values that are seen just a little bit better. And now we can change the color bar to something different. And here is the the Pyre image, the Pyre package here for the carbon color map. Well, we can see that it's distinguishing. What we have in here is clutter and noise. Now, probably some of the nearby trees versus the storms and precipitation out here in the greens and reds. And there are different examples to where we could view different elevations or a different field. So what the cross correlation ratio is that the radar will record back. Whenever it sends out the wave, it sends it in two polarizations, a horizontally polarized light and vertically polarized light. And it will record back the pulses in both of those polarizations. And what this tells you is how correlated the horizontal and vertical polarizations are in the return signature. So for spheres, they scatter both of these polarizations at about the same intensity. So we expect this correlation coefficient to be around 1. So here we can see mainly raindrops present here as we go into the volume, going with the correlation coefficients around 1. So in summary, within this notebook, we covered some of the basics of working with radar data. Now I'm going to get into a little bit more of the weeds here and get into what came here to present today about PyDDA. So as I mentioned earlier, how do we retrieve winds from these radar networks? So we have a network of radars, and they only retrieve the velocity of scatters in the direction of the beam. So for 3D winds, we need info from other sensors and models and physical constraints with different spatial temporal coverage and resolution. How do we integrate this information together to make such a retrieval? So here we do this using what's called the 3D variational technique, and that's what's commonly used in the field. So we find the winds the horizontal components and the vertical component that minimize this cost function, such that the estimated wind speed from the radar and the retrieved winds is minimized, and that we also satisfy physics such as the mass continuity and vorticity equation. And each one of these constraints has adjustable weights that determine what level you want to give, how much weight you want to give to that constraint. Now, for all this, you also need to have an initial state to work upon for this variation to work. Now, the implementation of this code is done in what's called Python dual Doppler analysis, or PyDDA. And it's an open source implementation of this 3D VAR retrieval that you could do. You can retrieve winds from an arbitrary number of radars. It's built upon the PyArt package that I showed earlier, and it's available on CondaForge, compatible with Python 3.8+. And if you have either TensorFlow or JAX installed, you can use it. Will be able to leverage the GPUs that are present on your machine. So here's an example of some of the wind retrieval that you can do using using a constraint called the high resolution rapid refresh. So what this is, it's a forecast model that the National Weather Service uses to predict storms within the next 12 hours or so. And it's done at basically, it's a weather forecasting model. It's run at about 3 kilometers resolution, and it's run every hour. And it adjusts in the current radar observations to try to make this forecast. In addition, we have 2 radars present here, and this is over the coast of North Carolina. One over here over LTX, and then the MHX radar coming down here. So what we are showing here are the winds with the estimated rainfall overlaid over the radar estimated rainfall rate. And these wind contours represent whether we're in gale force or storm force winds, with the red being gale force and the storm being, and the blue being storm force winds. And what we can see here is that PyDDA is able to resolve some of these localized the winds in these localized bands that are coming in through Hurricane Florence as it approaches into North Carolina. So I want to move over next into the example notebook, what I have available. So when I will go here, just escape, go back. Oh no. I gave somebody a heart attack. Well, now for the main event here. Well, so PyDDA is an open source package for retrieving winds from multiple Doppler analyses. So you're going to use it's a 3D variational technique. And then here I summarize again what the variational technique corresponds to for your wind field. And it does it by minimizing this cost function related to these various constraints that I mentioned earlier. So first, in order to get PyDDA, we'll have to import the necessary libraries. To give it here a minute. And it has go ahead and uploaded PyDDA. So for this case study, we're going to actually look at a case in northern Alabama that's where we had what we call mesoscale convective system, or what some people may call it's a line of thunderstorms with supercells out ahead of the main line approaching the Huntsville, Alabama region. So we're going to look at this case and we're going to be able to see how PyDDA is able to write out some of the updrafts that are in this storm, as well as some of the structure of the winds that we have. So first, we'll load our ARMOR data. And then here, what we'll do something called, earlier what I mentioned what we have to do is called de-aliasing the radar data. Now, what PyArt has is a function, and it has an algorithm in here to do the de-aliasing correction that I had shown earlier, called de-alias region based. So we're going to use this snippet of code here to do to go ahead and do this de-aliasing correction within just a couple of lines of code, just to ensure that our Doppler velocities are representative of the structure of the storm that we have, and that we don't have these aliasing artifacts affecting our input winds. So now we want to just quickly give a sanity check for our data. And here we have the data from the ARMOR radar being plotted over here. with the supercells out ahead of it here, and then the line of thunderstorms right behind it. We also look at the corrective velocity values, and here we can see that we don't have these. What we have here are more smooth transitions within the Doppler velocity, where we expect the Doppler velocity because of the direction of the winds to shift smoothly from about -30 to 30. We still have a little aliasing over here, but we're only going to be retrieving the winds from inside this box over here. So I'm not as concerned about potential artifacts from this radar over here. But we have done some cleaning up of the wind radar data here, just using some of the one pass de-aliasing step. And then now we're going to go and remove some of these other speckles over here, including these noise artifacts and clutter, by using the despeckle function. And that makes this cleaned up even more, to where now we have probably the most amount of these artifacts in the radar data removed that we can have. Next, what we have to do is to take that radar data. And what the radar records, it records the data in its native coordinates. So it records it in antenna coordinates. We have to convert it to a Cartesian grid. So what we're going to do here is PyArt has routines for doing this too, called map grid from radars. And it will take this radar object and it will make a grid. And it will put it in a Cartesian grid so that we can do easier analysis with the radar data rather than in its radar native coordinates. So this will go ahead and make that grid, and it will convert it to an X-array object. An X-array here, X-array is a package for reading in that CDF data. Then the X-array data set contains all the dimensions, coordinates, as well as your different data variables with the different dimensions that are in metadata that are in them. So this here is showing that the grid here has some of our differential phase and spectrum width and corrective velocity values. And we can actually use X-array even to do plotting of the data at these different levels by just doing data set ISO, that reflectivity in this case, .plot. And then here we have that same, we know that the gridding, we still see the same structure of the storms at the 500 meter mark. And if we go at the 115, so we're looking here at a cross section to the storm, we can see a vertical cross section of the gridding where and it looks here we have a fairly reasonable structure in the gridding where we don't have a lot of discontinuities in the radar data. One of the things you have to watch out for when doing this is you can get the radar data becomes more sparse as you get further up. So you have to make sure you have a continuous grid when you're doing some of these retrievals. Next, we can load the NextRad data. And this is available on Amazon Web Services under the NOAA NextRad Level 2 bucket. So you can actually just use you can actually go ahead and just use download it right off of S3 and download the NextRad data. And they have all of the NextRad data for every radar that's ever been stored, that's ever been done since, I believe, 1992 is when the NextRad radar network started. And that's all stored on Amazon S3. So we can actually, PyArt has native functionality to be able to load from S3. And we'll look at the 7th file over here at this time step, and it will just load that file right from the S3 bucket. So this is the second radar we're looking at. This is just the NOAA weather radar for the same time period. And we can visualize these storms over here again, another view of these as we come through. Now the NextRad Level 2 data also need to be de-aliased as well. So we do some of the same corrections to that data we've done before. We'll go here. And we'll visualize the grids that come out of that. Corrective velocity. And this looks like a good corrective velocity field. Now, the next step after we get our data prepared for the variational retrieval, we now have to have an initial guess of the wind field, the cost function minimization. So PyDDA has support for various initializations, including weather balloon data or even model data such as WRF or other forecast models, to where you could go in and put in a model, but go ahead and put one of these for your initial state. In this notebook, I'm going to use a Raywood side or weather balloon launch, where we have weather balloon data that was done just a few hours beforehand to get the initial wind field, and it'll give us initial guess for our variational retrieval. So this code here will load in your wind data that is present, and then we use make wind field from profile to make the initial guess. And then the core function here is done using retrieval.get DD wind field. And there's many potential keyword inputs that you could customize here, including all your weights and all your initial wind fields that you apply. You could do different filtering and even do different engines for doing the data. Now, what we're going to do here, I've actually, this step here will probably take about 15 to 20 minutes. So thankfully what I've done is I've went ahead and preloaded the data. That was the result of this retrieval, so that I'm not taking all the time here to go ahead and just do the retrieval while I'm spending here talking. So PyDDA also has some visualization routines here where we can look at the horizontal cross-section, for example, through a quiver plot. And we can do different types of streamline plots, bar plots, and we could go through a quiver plot of the storm by just doing horizontal cross-section quiver. And then here we can see winds flowing to the northeast. Now, what these lobes here are what I call the dual Doppler lobes. Though we get the best data quality if we have the radar beams that are perpendicular to each other. So in these radar lobes, the radar beams are sufficiently perpendicular to each other, so that we can have one component of the wind field measured over here, and then its perpendicular component measured at that same point. So therefore we're able to get more of a 2 to 3D view of the wind. So what we have here are winds flowing to the northeast, and what these contours represent are where updrafts are present. So we can see that it's resolving some of the updrafts that are forming these storms as we go through, including this updraft forming is here indicating probably some new formation out ahead of the supercell that we wouldn't be able to see yet with just the reflectivity alone. In addition, we'll also look at some quiver plots from a cross section, and you can see it resolving the updrafts going through here at around 10 to 12 meters per second that are then just preceding the downdrafts that are then forming the storm. Or we can view a horizontal cross section here with wind barbs. And what this shows us over here are it shows us here are the updrafts that are present over here with winds coming from the southeast. So what else did I have here today? So I think from here, another thing I wanted to show today, in particular, this is a part of tools that are part of what we call the Open Radar Science community. And we have a main webpage for this called openradarscience.org. As we copy. And I will go ahead and so what this is a community platform for free and open source weather radar software. So there's all these different projects that are part of the Open Radar Science stack, including PyArt. Well, and this is another radar processing package called BaltRad. We also have the PyRad package here. All these are different tools that you could use to process your weather radar data that are all available on the Open Radar Science website. In addition, we've had various workshops where you could view various tutorials that we presented, including one we presented last year down in Locarno, Switzerland, as part of the ERAD 2022 Open Short Course. All the different tutorials that are here available online. If you want to get familiar with the different radar packages and how to use them, and for all these tutorials, and we'll have the AMS, we'll have the one I showed you for AMS 2023 uploaded probably very soon. In fact, I could post the link in the Zoom to it right now. But if you go here, you can launch a Docker container here that will actually a binder that will go in and load the environment for you. And then once you're able to load up this environment, then you can execute the Jupyter notebooks on the cloud and be able to learn how to use some of these packages on your own as you go ahead and start learning about how to process your weather radar data. So another resource I want to go to is the Open radar science.discourse. And what we have here is, so this is a discourse forum where anybody who's using any of these open radar science tools can ask questions, and then those of us who are part of the open radar community can help answer them and try to help you get you on your way to analyzing your radar data. So I would encourage, if you ever want to use the open source radar tool stack, to join the discourse group where and come introduce yourself and meet us, and don't be afraid to ask questions. And I think that will be, if anybody has any questions, I think that's what I had for today. And I'd like to thank everybody for attending the talk. You first. I will say what I've analyzed for a similar radar. So we had a C-band polarization radar in Darwin, Australia. It took data from 1998 to 2015, and that took 27 terabytes. Yeah. So if I mentioned the next rad data is probably, I would have to guess it's on an older, since it's for probably 100 radars across the United States, you're probably talking petascale. Well, right now all of that data is on Amazon S3. Yeah, it's on AWS. Yeah, all the next rad level 2 data is on AWS. Mark, you had a question? Yeah. Yes, we have a. Yes, so we have started to embrace Python as a standard language. Over the past 10 years, we've seen a pretty big increase in the use of Python, and up to the point where it has its own conference at the AMS annual meeting on how to use Python for atmospheric applications. And even it has a SciPy track as well. So, and there was a question online that I saw. It was how the radar was collected. Yeah. So as far as how do we ensure if the methodology is correct? So a lot of times what we'll do, sometimes we can verify with the radar wind profiler and do a comparison of the vertical velocities against the radar wind profiler. Another way to just validate is to use what we call observing system simulation experiments, where you take a model simulation, you simulate a radar inside, and then you actually perform the retrieval on the model simulated radar, and then compare it back against the model winds. So it's like the model is your correct answer in the radar space. So that's a wild concept, but that is usually the way this methodology is validated. Yeah, there was a question online I saw. It was about how is the radar data collected, I think. We look at. Yeah. I don't know why I'm doing it that way. Bruce Sanders asked, where does the radar data come from? You talk about a little bit how the data is collected. So the radar data, as you have a radar deployed out at, for example, if we have a NextRad radar, what it's going to do, the actual thing that it's the actual signature that it's collecting are phase signals in the IQ. Now, those are the very raw data. Now, those pulses then have to be processed into interpretable radar moments by atmospheric scientists, and those are usually done at the actually NOAA will just store that raw data, and then they'll do that processing on their machines go ahead and process that level 1 data up to level 2 data. As far as talk about how the data is collected through various field campaigns, it's also collected as a standard operational network for NextRad. You can even take a mobile radar, put it on a truck, and then you could go ahead and, if you're an example, want to scan, for example, if you want to do something like Vortex, where you want to look at winds inside a tornado, you could take all these different radars, put them in trucks, deploying them out near the tornado, and then you could try to go ahead and do these wind retrievals out there. And that's what's been done for Vortex and Vortex 2. Question? So one of them was actually based upon the observation. So if you were to simulate a radar if you had a radar sitting inside there and it's going to collect it, you had the U and V value. You would the first one was, what would the radar record if you had the 2D wind or 3D wind present at that point? Then the other one was based off it's based off of mass continuity. So basically assuming that mass is conserved throughout the volume. So what that does is that when you have convergence, it will actually when you have converging air in the 2 dimension of space, the air has to be pushed upward or downward, depending on when you're converging or diverging. So it's going to resolve that as a physical rule. Yeah, that's actually why we do the reason we do the weak variational retrieval like that, what we call weak, is because we know that there's uncertainties in the observations that could exceed that sometimes if we do a strong variational retrieval, it doesn't take into effect the potential uncertainty in your observations. So we do this in a more of a weak manner to try to take that into account. Question? So I think there are some radar packages. Although I'm not familiar with ones that are. The ones I'm familiar with are in Python and C. Is the other way, like LROSE is written in C, though it has a Python wrapper around it. As far as data availability with NextRad, as long as you cite it's government public data, you can just use it. So NextRad radar data, anybody's available with it. There's no restriction on it outside of you have to cite the data. It's a government service provided to the public. Now in Europe, on the other hand, that's a different story because they privatized their radar network, so you have to pay. And in the US is actually the leader in making publicly available radar data available for the public. Question? No. So we are not collaborating with AccuWeather in any capacity, as far as basically. I mean, they do. I mean, I don't want to say too much about outside of. It is difficult to predict the weather beyond 10 days due to initial conditions in your weather forecast. The sensitivity of those models to the initial conditions really starts to show itself in about 10 days, and making a point forecast over a region becomes incredibly difficult to do. So I would not trust a point forecast above 10 days. I will not say anything about specific products or anything like that other than that. NASA has actually used it for GPM validation and validating some of their vertical velocity retrievals for GPM. NOAA has not. I don't think NOAA doesn't really do multi-Doppler in anything. So mainly because the computational expense is pretty high. But now with GPUs being enabled and that a lot of the software hasn't caught up to the technology. So maybe in the next 10 years or something, something like this could, if I have if tensor, because I could do with on a GPU, I could do this retrieval in about 20 seconds versus on a standard computer, it takes several minutes for one time step. And if you parallel GPU system, eventually, if we get to the point where those become more standard and for like NOAA or something, they may be able to provide a product like this. But that's still, I think we're still years away from that. And even then, doing these, a lot of times you do have to do some manual intervention for these retrievals. So that would be a difficult problem. We usually use these more for research. Yes, that is I do mean cost function. What I do mean with that, we are minimizing an error term to determine an optimal solution. We're minimizing the error, we call it the deviation from observations from the mass continuity equation, because vertical velocity, or even ensuring that the wind field doesn't have noise in it by minimizing the Laplacian of the wind field. So it is according to an error solution. So right now I'm involved in a project called the community oriented. It's a community oriented climate and urban research studies called PYDDA. And we're going to be deploying we deployed some Doppler lidars that look at that are going to look at winds and turbulence over about 30-meter scales in the city. So we're going to be looking at doing some experiments with those to see if we could get 2 to 3D winds out of multiple Doppler lidars. And I want to be able to import support for those into PyDDA. So that's one of the next things I'm excited about. Also, I want to incorporate a complex terrain as a lower boundary condition. That's another aspiration. They'll fly up to, well, we measure more pressure, but they'll fly up to about, usually they'll hop at about probably 15, 20 kilometers usually. No, no, yeah, that was no, that was not a weather observation balloon. No, they'll just go up and they'll pop. Yeah. And then actually, you can find these Brayward songs on the ground, and you're supposed to put them in a mailbox, but I don't know how many people actually do that. They just come up as junk in the ground. Yep. Oh, I have. I did play around a little bit with using a convolutional LSTM, and there are some research on this that are using different types of CNN networks to try to predict the next time step from the previous time step and try to track these cells as they go through as a way to do a quick nowcast, because that would speed up our ability to nowcast storms. You could get to about a half hour now, which is actually decent considering you could get, we still haven't gone past about an hour with that, but I think they've gotten about a half hour using CNNs. All right. Thank you. Thank you for hosting me. My pleasure to talk today.